So I'm Stephanie WALDHOFF, and I'll be presenting on behalf of several authors on this work. And this morning I'm going to talk about looking at the marginal damage of methane emissions through the ozone impacts on agriculture. So the motivation for this is that due to its contribution in climate change, we know that methane contributes to physical, economic impacts in many sectors, including agriculture, energy, human health, and biodiversity. But methane also reacts in the atmosphere to form tropospheric ozone, which independently generates damages to human health, climate, biodiversity, and crops and vegetation. So while methane is a relatively short-lived greenhouse gas, it's longer lived than all the other ozone precursors. And due to this long lifetime, methane emissions will affect ozone concentrations globally, regardless of the location of the emissions. So methane emission changes in one region will have direct impacts on ozone concentration levels all over the world. And so a change in emissions in one region will cause global changes in damages or benefits. The marginal benefits of methane mitigation on climate and health have been used in several cost-benefit analyses by the US government, such as the 2016 oil and gas and landfill new source performance standards, and also more recently in the 2020 oil and gas rule. So the work we're presenting here can inform such rulemakings through a more complete accounting of the benefits of methane mitigation or damages from emissions that include the marginal impacts of ozone on agriculture. And in this case, because ozone damages are systematically negative for crop growth and productivity, it's a little more clear-cut than the damages from climate change on agriculture. So the methodology we're using here, we calculate the marginal damages using two models, GCAM, the Global Change Analysis Model, which Ying just introduced. So I'm going to skip the explanation of what that model is. And GCAM gives us a baseline emissions for ozone precursors and agricultural production and prices. And we use the ozone precursor emissions in the TM5 fast scenario screening tool to transform those emissions into ozone concentrations. We then re-estimate ozone concentrations using an additional pulse of methane and calculate the change in the relative yield loss using the method and parameters from Wang and Mazeral 2004. And then the resulting economic damages from the pulse of emissions are equal to the revenue times the relative yield loss. And the damage per ton of methane is the total damage divided by the emissions pulse. We also test the sensitivity of the results to several different factors. Because we know the value of agricultural production is going to depend on the demand for agricultural commodities, which will then depend on population and GDP. We test the results using 5 different scenarios, the shared socioeconomic pathways, and with SSP2 being our central scenario. We also test the effects of the emissions pulse size, for the central scenario being defined with 10% of projected US emissions, methane emissions in 2020. Those are the GCAM emissions, not the COVID adjusted ones. And 2 sensitivities using only 5% or 15%. Because the cost benefit analyses need to include the value of future changes in emissions as well. In addition to 2020, we also estimate the marginal damages for 2030, 2040, and 2050. And finally, we test the multiple discount rates to calculate the net present value of future damages to the reference year. And so our central scenario uses a 3% discount rate, and we also test 2% and 5%. So our central scenario is defined for an emissions pulse of 10% of US methane emissions in 2020 under SSP2 with a discount rate of 3%. Using the TM5 FAST model to calculate the changes in ozone concentrations attributable to this pulse of methane emissions, we can see that our central scenario ozone concentrations could increase by up to 0.1 parts per billion by volume. And we see these increases in concentrations are primarily in the equatorial regions due to the higher level of solar irradiance there. And this increase in ozone concentrations has different impacts depending on the crop. But we see the highest relative yield losses, again, are concentrated in the regions with the largest changes in ozone concentrations. And we see that soybean and wheat are much more negatively impacted by the increased ozone concentrations than maize and rice. And again, the relative yield losses are defined by Wang and Mazeral with crop-specific values for parameters A and B. So the results on the marginal damages, we estimate total crop damages per ton of methane for 31 GCAM regions and find global marginal damages to agriculture are about $452,010 per ton of methane in our central scenario. Of this, just under $100 per ton occurs in the United States, with our EU 15 region, China, and India being the next most heavily impacted regions. The figure on the right shows the temporal pathway, and we see that it's not completely smooth, but that's because the damages depend on the underlying ozone concentrations, which vary across regions over time, and where the production is in these different years and what the prices are. And this slide shows the range in emissions across our different sensitivities. And we can see that there's a fairly small range of values across these sensitivities, varying from about $350 per ton of methane on the low end to about $500 on the higher end. First, looking at the pulse size, we see that the larger pulse size has only a very modest effect on the damages, while a smaller pulse decreases damages by about $90 per ton. And this has to do with the nonlinear effects of ozone on agriculture. For the SSPs, we see that the scenarios with higher reference yields, those are SSP1 and SSP5, have much smaller changes in damages relative to SSP2, where the scenarios 3 and 4 with lower rates of improvement have higher damages. And then with the discount rate, we see there's not huge effects like we might expect from something like the social cost of carbon, because methane is much shorter lived and so less sensitive to the discount rate. So under our central scenario assumptions, we find that the marginal global crop damages, again, are about $452,010 per ton of methane. Compared to some other estimates of damages from the ozone impacts due to methane emissions, we see that the agricultural damages are about 35 to 40% of climate damages, as estimated by the social cost of methane, a couple different papers, and about 60% of the damages from increased mortality. The sensitivity of our estimates to scenario, discount rate, year, and emissions pulse size is relatively small, ranging from about minus 20% to about plus 10% of our central estimate. And a relatively large share of these damages occur in the US, about 22% of the total global damages, and this is due to the US's role as a major agricultural producer, as this is compared to the mortality damages, where only about 11% of the global damages are in the US. And finally, I want to note that these damages are for agricultural crops only. They don't include forest products or damage to pasture or other ecosystems, which could be done in future work. So let me see, do I stop sharing now? I want to say thank you. Trying to get back to this.
I'm trying to come back up. Thank you, Stephanie. That was great. Are you open to questions now?
I am open to questions, and I'm trying. Can you guys still see my screen?
I can see you. I can't see the.
You can see me. Oh, yeah. Okay, good. I wasn't sure if I stopped sharing or not. Thanks.
Great.
Yeah, so I can take some questions now.
Yeah. So you have a question, which actually was one similar to one I had, which is whether or not land use and crop type change is taken into account with the methane pulse.
Yes. You mean whether it changes, we re-estimate the land use change with the methane emissions?
In response, I'm assuming that.
In response to the ozone damages? No, we actually don't. We just take it, we're assuming it's a marginal change. So we're just doing it based on the reference production prices, as opposed to re-estimating through GCAM what the change prices and production would be.
Okay, great. And then related to that, I was going to ask you about, so the yield loss calculation itself is not including those kinds of effects. So there's not sort of an adaptation behavior of any kind reflected, and that's
exactly.
So you're looking at overall production, but it's sort of fixed across the pulse and with and without. Okay. There's another question here. I was trying to remember how to get people so that they could ask their own questions, because Claudia has a bigger question. I don't remember if I can remember how to do that. So Claudia, I don't know if I'm able to give you, do you remember, Stephanie, how I do that? Maybe I'll just read Claudia's question.
Yeah.
So Claudia has a question, says her understanding is that people find a negative feedback of ozone production from warming. So would it make sense to also do this analysis accounting for this feedback? And would it be possible?
That's a good question. And I would actually, I don't know if John San Pedro is on, and he's the one who's been doing this work, particularly in the TM5 FAST model, which is where we're estimating those ozone concentrations from. And I do not actually know myself whether that would be included, but I think it is not. And John, if you're on, feel free to weigh in, but I think it's a really small enough amount of emissions changes that we're talking about here, that there probably would not be a large effect, because we're just talking about a 10% change in US only emissions in 1 year.
Right.
It's not a continued pulse. It's a shock in 1 year.
And presumably there's interaction in terms of with the climate. So you're getting both an ozone and a climate related impact that are both playing. Oh, they're not. Okay.
We're not because the social cost of methane presumably is supposed to include some of those agricultural impacts. So we were trying not to double count.
Oh, I see.
Only looking at I mean, we have thought about doing work that includes both of them, and we can do that. But in this case, because one of the questions we're trying to look at is how this could be used in regulatory decision making. We didn't want to double count, and if we did both of them, we'd be open to double counting there.
Great. So why don't we go ahead and you can stay on for one more question. I've got one more for you to think about while Elizabeth gets on screen. She's now ready. Okay. And Elizabeth, you can go ahead and get your slides up. And then my last question was about the location of the pulse. So since we're talking about ozone and not so much about sort of the broader global mixing, does that matter if you model the pulses coming from a certain place?
It doesn't, because the methane itself is well mixed. And so the additional effect of methane on ozone concentration should be well mixed itself, but the ultimate concentrations will depend on the underlying concentrations of other ozone.
Yeah.
So you can see a different change across regions, but it's all from the same methane related ozone. Does that make sense?
Great. Yeah, I think it does. Yeah. All right. Thank you, Stephanie. That was great. Now we're going to turn to Elizabeth. Elizabeth's going to be talking about water quality interactions with agricultural nutrient management. So Elizabeth, over to you.
Thanks. Can everyone hear me?
Great.
Can you guys hear me?
I can hear you just fine. You sound great.
Okay, great. Thanks. Yep. So I will be speaking. Great. So I will be looking at water quality, and specifically the problem that we are addressing with this work is a global problem of excessive nutrient pollution, in particular phosphorus in freshwater bodies entering water bodies, and eventually leading to harmful algal blooms, particularly in shallow bays and bayments. The spatial extent of the study that I will be showing you is a watershed scale model centered in the Northeast US on the Canada border. We have a relatively small water body that is also fairly shallow and experiences excessive algal blooms almost every summer. The watershed is is in the US and Canada, roughly 58% and 42%. And this problem is obviously compounded by climate change, rising temperatures, and increasingly extreme events, particularly precipitation, but also drought in the Northeast US. So I will focus on kind of this one-dimensional phosphorus reduction analysis, and I'll show you how we are extending the scenario dimensions as well. But to start, we are leveraging a process-based integrated assessment model to understand system-level phosphorus loading reductions to the lake under future climate scenarios. I like to call this the magic spigot approach because we are just magically turning the phosphorus level down on the loading in the lake. And the model we are using to do this is shown in schematic here. We have the specific experiments I will show you use only a portion of the model. It's a feed-forward version where we have regional climate driving the hydrologic system, which we model using RHESIS, which is a standard hydrologic model. The Biome BCG model takes care of the biogeochemistry, the A2EM lake model, which is what we'll see results from. And our team in-house built a land use model, which we call the adaptive land use and land cover agent-based model, which simulates both land cover change and, land cover change in this case will be the primary driver for the land use model. So our hypothesis is that at some point, our system will start to respond to a reduction, a TIR, and become increasingly resilient in terms of its HABs events, and that at another point of increased reduction in phosphorus will become even more extreme, more resilient to those extreme events in the future. And this is kind of our one-dimensional question. What are those values of phosphorus reduction that will lead to this increasing resilience? So we run an ensemble scenario suite, and I will show you just a few important details. The temperature of the ensembles that we are using, the ensemble climate members, are gradually increased over the model period, while the precipitation is relatively constant, but you see a little bit of a rise over at the end of the time. So to understand whether or not the blooms will go away, we compare the baseline period, which was 2001 to 2010. We see that looking just at the phosphorus, The red line is the mandated from the federal government objective for the water for the bay that we're interested in. And you can see that during the baseline period, we were well above the objective target. If there is zero reduction, we project that the phosphorus in the bay will continue to be above that target. And you'll notice that not until we are reducing by 40% of the baseline load do we start to even see an improvement, although we're still above the target phosphorus level. And during the period, we have to reach 80 to 100% before we are below the target phosphorus level during any of the period. So if we look at the chlorophyll concentrations, which are a proxy for the presence of harmful algal blooms, we see that the bay during the baseline period was relatively eutrophic. And again, not until 80% or 100% do we start to see a reduction below the eutrophic line and approaching the WHO's standard for mildly eutrophic. We suspect that this is a result of both internal loading and increased warming in the bay waters as a result of climate change. So we have two competing physical processes that are limiting our potential success here. So if we go back to our hypothesis, we can update that and suggest that that the regulatory target of 64.5% reduction probably isn't going to get us to the resilient state that we are looking for, and that it's likely going to be compounded over the time period that we're looking at. So quickly, we likely need a more aggressive target in this case, but there are also significant lags in the system that we're observing, and it's possible that more time will be required to achieve the resilience that we are looking for. Now that we understand kind of the magic spigot, we are setting up additional scenarios that look at the who and the how of reaching these kind of magical reduction numbers. And we look at the landscape and who is contributing to the phosphorus loading in the bay. And we see that agriculture is a significant contributor. These are actual pictures of our lovely state. Forest contributes some, development contributes some, streams actually, when they're eroding, are contributing a fairly significant portion. And each of these actor populations are being asked to implement specific practices, best management practices that vary depending on the group and are intended to reduce the nutrient load to the bay to the levels that we previously saw will be necessary to achieve that objective resilience. So our next set of scenarios will look at both BMP adoption and the reduction potential, agriculture being a significant portion of that, as I'm showing here in the black dashed line. And the runs that we'll use to do this will focus on best management practice adoption using social psychological adoption science methods and reduction efficacy based on that adoption. Since I'm running out of time, I think I'll skip some of this detail, but we're using the theory of planned behavior to actually implement this in our agent-based model. And I'm happy to go over some more details later in the comments, but results are forthcoming. So I'll take questions on what I've shared so far, and hopefully that was a teaser for upcoming papers.
Thank you, Elizabeth. That was a teaser. I'm interested, so definitely got one.
Sorry to interrupt. Can everyone, all the presenters, make sure they have muted themselves or press the red telephone button, because we are getting some background noise from someone. Thank you.
All right. All of it's coming from our speaker.
Sorry.
So thanks, Stevie. So I'm just looking to see if we have any questions. We don't have any new questions. And Hélène, you should go ahead and get your slides loaded. In the meantime, I will. I've got a question for you, Elizabeth. So I'm looking at my questions.
Yeah.
Do you think there's a way to separate the internal loading from the climate? You had mentioned both things being factors. To do some sort of like decomposition?
Yeah, I didn't have slides to share the specific factors that we looked at to kind of come up with that determination, but we do have tons of data. We have the lake model is you can decompose the physical stratification of the water column and determine where the sediment is coming from during the study period, and obviously the increasing temperatures are important as well. Although we have folks who are looking at the impact of the drought versus really wet years and the sequence of those years and their effect on the likely have presence as well. So there is a lot of complication that is necessary to tease apart to get a really good idea of what's happening.
It'd be really interesting to sort of understand how those things are interacting with each other a bit more. So one more question. I think you have a little bit more time. Was just, and this is actually related, I guess, to your forthcoming work. So maybe you don't have much to say about this, but my one takeaway for me in the first part of your presentation was that we needed 100% reductions, and to really be able to get to those resilience levels you were talking about. And then you started talking about the different sources in the second portion of your talk. And I don't know whether you already have an impression about what are the hardest to reduce sources if we're trying to get to 100% of everything.
Well, the hardest, I don't know that 100% makes a whole lot of sense in the long term, because that's physically kind of impossible. I think the more likely answer is that it is going to take longer, more temporal, more time to process the excess nutrients that is existing in the bay, and go more towards a better equilibrium. The system needs some phosphorus. The question is kind of how much in a dynamic sense. The question of what's going to be hardest is a kind of social political one. Obviously, agriculture is a very significant contributor. Forests maybe are going to be the hardest, but forests, the way they calculated the contribution of forests is somewhat potentially questionable. You kind of add up everything else, and then the forests are what's left. So, the politics of reducing phosphorus loading from agriculture are obviously complicated. I think it runs the gamut.
Okay, great. Thank you, Elizabeth. We're going to move on to Hélène. And Hélène, so Helene's going to take us in a little bit of a different direction, talking about climate change and migration. So over to you, Hélène.
Thank you. Can you hear me well?
I hear you just fine. Yep, sounds great.
Great. Yes, so this project I'm going to talk about today deals with the effect of climate change on immobility. This is a joint project with Michael Oppenheimer at Princeton and Marc Fleurbet at the Paris School of Economics. So the motivation behind this work is as follows. You probably have heard quite a bit in the past few years of discussions of the potential effect of climate change on human migration, and in particular on international migration. Yet there has been really way less discussions about immobility although migration and immobility really are two sides of the same coin, both migration and immobility are not always the result of an actual desire either to move or to stay. They can be a choice, so they can be closer to more of an involuntary consequence of a given context. So while immobility can be a choice, we know that resource constraints can actually limit someone's ability to migrate. And that's because migration, and in particular international migration, requires resources, whether economics or social or health related. The people who move are the people who are able to do so. And so these populations who find themselves in a situation of immobility due to a lack of resources are what I'm going to talk about today. Now, the effect of climate change on mobility and immobility is quite complex. It can play out both directly and indirectly through various channels. And depending on the context, climate change is going to either increase or decrease migration flows. For instance, here on the left picture, this is kind of an illustration of the fact that migration is a widely used adaptation strategy to climate change. So you might think that over the century, with more and more impacts, we will see an increase in the use of migration as an adaptation solution. But on the other hand, the picture on the right here illustrates the fact that climate change depletes resources, in particular in some of the most deprived areas. So you might think that with increased climate change over the century, there will be a decrease in the number of people who are actually able to migrate. And so this is what this project focuses on. We're trying to quantify how much will climate change constrain international migration. So we go about it in two steps, which I'm going to walk you through. First, we devise a model of international migration, and then we're going to come and embed this migration model in an existing integrated assessment model in order to capture the effect of climate change on resource deprivation and subsequent immobility. So our model of international migration and remittances, we developed one, and just a note here to say that we model all international migration, not just the one that is purely climate related. So major drivers of international and long-term migration can be classified in three sets of drivers. You first have economic opportunities, so people are going to move somewhere else in order to earn higher wages or to be able to send money back home. When choosing the destination, there is this notion of proximity between origin and destination, so whether geographic or cultural. And finally, the migration costs. And here we're going to look in particular at the resources that are necessary to migrate. We're going to use what is called the gravity model. This concept of gravity is just this idea of bringing all those push and pull factors together in one framework. And the specificity of our model is that we design it at the income quintile level. And the reason for that is because that way we're able to capture the differentiated resource deprivation of the various populations. So we're going to model bilateral migration flows at the income quintile level in two steps. First, we're going to compute the number of people who are going to move from a given origin and who are going to come from a specific income quintile and go to a given destination. And then we're going to distribute that number of people over the different income quintiles at destination. The first part of the model is our gravity structure. So that number of people is going to be a function of population sizes of the two locations. In green here, you have the resource constraint, which we're going to illustrate as the income per capita at origin in the specific income quintile that we're looking at. Then the dark blue ones are the economic opportunity components. So we first have the ratio of income per capita between destination and origin, which illustrates the pull towards richer locations. We have variables on the typical remittances that are exchanged between the two locations, which highlight this notion of pre-existing migration networks between the two locations. And then in green-blue, we have the proximity components, so the geographic distance between the two locations and whether they speak a common official language. Once we have this number of people here, we're going to distribute it endogenously over the income quintiles at destination. And that distribution is going to be a function of this ratio of per capita incomes between destination and origin, illustrating, again, the relative development levels of the two locations. We're going to estimate a model using past data in the interest of time. I'm not going to go too much into the estimation. And then we're going to use this model to project migration flows in the future. And in particular, this is where we're going to come and couple this model to an existing IAM, again, to try and capture the effect of climate change on resource deprivation and subsequent immobility. So here we work with FUND, which is an IAM, one of those IAMs that has both the emissions and the damages feeding back into the economy. FUND has some regional disaggregation, with the world divided into 16 regions. And what we do here is that we come and couple our migration model at the income quintile level to the FUND model. And for that purpose, we need a version of FUND which has income quintiles. So for that, we're going to use the approach that has been developed by Francis Denick and others in their 2015 paper. And in particular, that approach involves distributing two key parameters on the different income quintiles in each region. First, we need to distribute the mitigation cost. Here, we're just going to assume in this project that the mitigation cost is going to be proportional to income. So that means in a given region, everybody is going to pay the same share of their income for reducing greenhouse gas emissions. And then we need to distribute damages. And here it gets trickier. We need to understand to what extent damages are going to be affecting more the poor versus the richer. So in the literature, there is no, at this point, clear estimation of the exact extent to which damages are going to be affecting the poor more than the rich. But what it seems like is that damages are expected to be regressive, so affecting the poor at least more than the rich. Again, because we don't know exactly to what extent that happens, here in the paper, we use three different assumptions for how damages are distributed over income quintiles. First, we're going to assume that damages are proportional to income, meaning in a given region, everybody pays the same share of their income for damages. Then we're going to assume that damages are independent of income, meaning in a given region, everybody pays the same amount of damages from climate change, regardless of their income level. And then we have an even more regressive assumption, which is that damages are going to be inversely proportional to income. So in the paper, we show results for all three, but here I'm going to focus on the independent assumption, which is likely to be conservative. And then in order to quantify this effect of climate change on immobility, what we're going to do is we're going to compute the number of migrants from the lowest income quintiles in each region, and we're going to look at the difference between that number for runs with climate change versus runs without climate change. We're going to look at a bunch of different scenarios of development and climate change. Here I'm going to show results for two scenarios, a medium one and a more pessimistic one with higher levels of climate change and higher levels of inequality. And finally, of course, our results are going to depend on how damages are calibrated. So in order to stress test our results, we're going to add a specification, including catastrophic damages, following Marty Weissman's work. So let me now show you the main results for this project. So here what I'm showing is the effect of climate change on outmigration of the bottom income quintile in each region. This is a result for 2100, and this is for the medium climate and development scenario. So what you see here, the pink shades are mean that outmigration decreases with climate change compared to without climate change. And the green shade means the opposite. So what we see here is that we find an effect of climate change on immobility in three regions, in particular Sub-Saharan Africa, North Africa, and the former Soviet Union, with a decrease in outmigration that reaches 10%. Now, when we look at a more pessimistic scenario, we find that this effect on resource-constrained immobility is increased in the same regions. And now when we look at more catastrophic damages, we find that the effect of climate change on immobility really is basically prevalent in almost all regions, and it reaches a decrease in outmigration of 20% in the North African region for the more pessimistic scenario. So that's quite substantial. So what that means to us, just to conclude, is that resource-constrained immobility is not at all going to be a rare event. Rather, we expect it to play really a key part in this climate migration nexus that people have been talking a lot about. From a policy perspective, what that means is that the populations who are going to find themselves unable to leave as a result of resource deprivation due to climate change are going to find themselves extremely vulnerable, first to subsequent impacts from climate change, and also more generally to increased risks derived from poverty. in terms of international institutions that would be helpful to deal with this question. So here are 3 of them: the Sustainable Development Goals, the UN Global Compact for Migration, which is a non-binding agreement that was signed about 2 years ago. And within the UNFCCC framework, the main relevant point would be the Warsaw Mechanism for Loss and Damage. None of these institutions at this point explicitly addresses this notion of resource-constrained immobility. I'm hoping that will change in the future. I'll stop here, and I'm welcoming your questions. Thank you.
Okay, you've generated some discussion and some questions. So let me start just right at the top. So there's a question here, just clarification on what constitutes long-term migration.
Yes, absolutely. So here, what we mean by long-term migration is that we don't explicitly model return migration, in the sense that perhaps, so we model migration in both directions between every region, but we don't specifically trace the individuals. So we don't know how long the people are staying. We just assume that the flows of people who are staying, who are moving, then stay in a given location. Oh, I don't know if what I'm saying is very clear. We don't trace the exact individuals, we just trace the migration flows. And so what that amounts to is somewhat assuming that the migration is permanent once the people move, they stay in their destination.
Great. Another clarification question about whether the model takes into account displacement by civil or interstate war.
No, we don't take into account specifically war, or in the sense that in our estimation, we don't trace that specifically. So we just assume that in our projections, the displacements that were taking place during the period of estimation are basically involving are keeping at the same level over the period of projection. It's quite difficult to disentangle in a quantitative way the effect of conflict on migration. I know the presentation right after me is about conflict. I don't know if the person's going to touch on that, but I'm looking forward to it.
And build off each other. So there's a pair of questions here. Some people are interested in the empirical work that estimated the migration relationships. I don't know if you could say a little bit more about that, and that might shed some light on their questions.
Yes, so the way we estimate it, so if I go back to, let's not bother. So the way we estimate it for the independent variables, so we need data on, so we estimate the model, at the country level using only one time period, and that's because it's very difficult to get good data on the income profiles of migrants. So we have data on several time periods for the migration flows, but we don't have data on several time periods for the income profiles of migrants. So we just use one time period, which is a limitation. And then so the dependent variables, the independent variables, for the data is rather easy to find. So we need data on income levels, on inequality levels, on population sizes, etc. That's data by and large that's available from the World Bank. Where it's more difficult to get data is on the dependent variable, which for us is bilateral migration flows per income level. That kind of data is not really available out there. So what we did was we built a data set based on what's available in the literature. So on the one hand, we used bilateral migration flows that were derived from bilateral migrant stocks estimates that are available from the World Bank. The derivation from stocks to flows has been done by several teams of demographers, so we use those exercises. And then we couple that data to data on migrants' income profile. And for that, we use the SSP framework. In the population projections, there are explicit quantifications of migration flows per education level. And using a couple assumptions, we transform the migrant flows per education level into migrant flows per income levels.
So I'm just going to give you a heads up for the bigger discussion period because I want to make sure that Victoria gets her time. So there's another question here, and you can think about it and decide if you want to show more. Some people are interested if you actually have regression details. So if you want to put up a slide or something when we get to the discussion period, we'll let you do that.
Thank you.
Also, they're interested in if you could say a little bit more about changes in the migration relative to today. So just to give us some context.
Yes.
in terms of how large the effects are that you're finding.
Thank you.
So anyway, that's a heads up. you can think about how to address that.
Thank you.
So thank you very much, Hélène. That was fantastic. Victoria, why don't you go ahead and load your slides?
Okay. Awesome.
Right.
Thank you, Steve.
Great.
So I am
Sure.
very excited to present my research in progress, Endogenizing the Costs of Climate-Induced Violence in the Optimal Management of the Climate, a merge modeling approach. So I'm an assistant professor of environmental politics at UVA, and previously I was trained as a political scientist and environmental engineer at Stanford. This project, which started and was developed as class projects in Professor John Wyatt's class, represents part of my research agenda to integrate political science into climate modeling. So, click. Great. So extent modeling work has integrated economic, technological, and biophysical processes that produce GHG emissions. And click. Political science has rarely entered the picture, although humans and institutions play significant roles in shaping policy outputs and outcomes. Click. Making reasonable assumptions about human behaviors can provide essential insights into alternative future climates. And click. It is very challenging, but I try. So for today's exercise, the concept, a political science concept that I try to integrate is, please click. And click one more time. Violence. So violence is destructive to social order and economic growth. It is a part of and is devastating to the human condition. Every year, 1.4 million people around the globe die from violence, and many more suffer from a range of physical and mental problems because of it. We live in a world that is currently struggling to respond to a ballooning number of increasingly complex conflicts, which forcefully displace record numbers of people, estimated at 65.3 million in 2015 alone, and pose record-breaking humanitarian needs. The annual total physical cost of violence is estimated to be $9.4 trillion, which is equivalent to 11% of the world's GDP. And interpersonal violence costs 6.4 times more than collective violence. Next slide, please. So some scientific studies have established an active link between climate change and the incidence of interpersonal and intergroup conflicts. According to these studies, climate change can contribute to violence in both direct and indirect ways. Click. Directly, hotter temperatures can increase the level of aggression, which often leads to more violence. And click. Indirectly, hotter temperatures and abnormal rainfall can affect crop yields, which subsequently affects economic growth and also the incidence of violence. Climate change can also influence government revenue and migration patterns, which subsequently affect the incidence of violence. And next slide. So this study connects the climate economy and the climate violence systems by putting forth, click, a new way of modeling carbon externality to endogenize the critical yet previously missing aspect of climate impacts, violence, click. The objective is to understand how any increased risk of violence associated with climate change may affect the trade-off in choices relating to carbon emissions. The objective is not to provide precise predictions or propose a new carbon pricing policy. Next slide, please. So fortunately for this study, I am able to refer to finely disaggregated and newly available data on the cost of a wide range and types of violence for different regions of the world. The estimates generated by political scientist James Furon and economist Anka Hofla are based on value of a statistical life approach. There are three general categories of violence: self-directed, collective, and interpersonal. The author's figures likely represent an underestimation because they do not consider self-directed violence. The psychological costs and additional costs associated with sexual violence are excluded. Some relevant costs are excluded when data is unavailable, and they're also not valuing the invaluable, such as decline or loss of social capital. Next slide, please. In their meta-analysis of the 60 most quantitatively rigorous studies of 45 different conflict data sets, Sandberg and Miguel estimated that, sorry, the previous slide. The previous slide.
Oops. Is that right?
Can we?
There's a table on
Can
it.
we see the previous slide, please?
Is that the slide with the table? Sorry.
I think it's the previous one.
This one. There's nothing in between those two. There's one with the data and then the slide with the table.
Oh, okay. Okay, so I might have sent the wrong version of the presentation. So there is an econometric relationship between climate change and violence being used in the study. Oh, actually, it's the right version. So based off of James Furon and Anka Hofler's estimates, I classify the different types of costs into the market and the non-market damages. So in the case of violence, market damages include GDP losses from war, economic costs of medical care, criminal justice system, and lost income. The non-market damages include deaths from war and also fear. And I calculate the cost of collective and personal violence as percentages of GDP for different global regions by market versus non-market damages. Next slide, please. So in their meta-analysis of the 60 most quantitatively rigorous studies of 45 different conflict data sets, Sandberg and Miguel estimated that for each one standard deviation change in climate toward warmer temperatures or more extreme rainfall, the median estimate suggests that the frequency of interpersonal violence rises 4%, the frequency of intergroup conflict rises 14%. And their results may be informative for understanding future scenarios of climate-induced violence because, next slide, please. Because growing unpredictability of temperature resulting from climate change will likely lead to sustained increases in violence. And next slide, please. The chosen model is MERGE. MERGE stands for Model for Evaluating Regional and Global Effects of GHG Reduction Policies. It is an intertemporal general equilibrium model that optimizes discounted utility. It has a relatively detailed climate module, allowing for sufficient flexibility for an alternative view on a wide range of contentious issues, including damages from climate change. It also covers multiple geographic regions of the world. So for this study, I opt for the benefit cost model because it seeks the socially optimal price of carbon given assumptions needed to internalize the externalities associated with climate change and maximize the net benefit to society. Next slide, please. So I begin with projection for the reference scenario where all variables other than the market and non-market damage factors are left to their default values. So since the model output carbon prices are unnormalized and the rise in carbon price over time is largely driven by economic growth, it is most worthwhile to focus on how much larger endogenizing the cost of climate-induced violence would increase the optimal carbon price. Hence, I calculate the ratio of carbon prices in the violence scenario and the business as usual scenario. The figure here suggests that internalization consistently raises the optimal carbon price by more than 0.8 times, representing a near doubling of the optimal carbon price during the 2020 to 2200 period. And next slide, please. So with the cost of violence internalized, the optimal path of the model shows a lower speed of temperature increase and associated rates of collective and interpersonal violence. And next slide, please. So to assess the normative significance of a slow temperature increase, I calculate the avoided damages from climate-induced violence as a percentage of regional GDP. The biggest beneficiary, as we can see from the figure, is sub-Saharan Africa, which is projected to avert about 0.1% of GDP loss from climate-induced violence in 2050, and the figure is projected to rise to 2% in 2200. And next slide, please. And I also conduct a series of sensitivity analysis And the first dimension along which I seek to test the sensitivity of the results is climate sensitivity, which, as we know, refers to the equilibrium global mean surface temperature change following a doubling of atmospheric carbon dioxide concentration. Its default value in MERGE is 3.5 degrees centigrade. The upper and lower bound values of climate sensitivity that I also explore are 1.5 degrees centigrade and 6 degrees centigrade. As shown in the figure, the relationship of a near doubling of the optimal carbon price due to the internalization of climate-induced violence costs holds across time in all three scenarios. Next slide, please. The second dimension along which I seek to test the sensitivity of the results is the GDP growth rate. I increased the default GDP growth rate in MERGE by 1% and 2% respectively. The figure shows that according to climate-induced violence costs nearly doubles the pricing of carbon externalities, and a relationship that remains robust across time and growth rate scenarios. And next slide, please. The third dimension along which I seek to test the sensitivity of the results is the willingness to pay to avoid non-market climate damages. For non-market climate damages, MERGE is built based on a highly speculative assumption that the expected losses would increase quadratically with the rise in temperature. By changing the willingness to pay for non-market damages, which is in itself uncertain, I can influence how much non-market damages are factored into the calculation of optimal carbon prices. The default WTP in MERGE is 4%, meaning that residents of all regions are willing to devote 4% of the regional income to avoid non-market climate damages associated with 2 degrees of warming. Since the figure could be lower in less developed regions of the world, I changed the willingness to pay to avoid non-market damages to 1% and 2% for the sensitivity analysis. As we can see from the figure, incorporating the cost of climate-induced violence raises the projection of optimal carbon prices to about twice as much as before under the 2% regional GDP assumption, and a bit about 3 times as much under the 1% assumption. Therefore, changes in pricing the carbon externality in the violence scenario vis-a-vis the BAU could be sensitive to the assumption about the willingness to pay to avoid non-market damages. And there are 3 more sets of sensitivity analysis which I have to skip in the interest of time, but I'm happy to talk about them during Q&A. So I want to point out there are 2 caveats in our interpretation of the results. The first is that the cost of violence are plausibly low bounds estimates, which would downwardly bias the estimates of carbon externality. A second caveat is that since the climate violence relationship coefficient in the study being used here, Xiang et al. 2013, is mainly based on local temperature deviations, which are likely higher than the global temperature variation, the estimates of carbon externality could be biased upward. So future research. Next slide, please. Next slide. Thank you. So for future research, I hope to utilize improved estimates of the cost of violence, which would be based on the country-level estimate of the value of statistical life, projected country-level weather trends, and also country or region-level climate violence relationships when such estimates become available. And since Xiang et al. 2013 provides one approximation of the true functional form of the relationship between climate change and conflict, future research can also utilize other functional forms in the modeling exercise, such as a linear relationship. I also plan to conduct similar analysis using other EMs and perform intermodal comparisons of results. So if anyone on the panel or in the audience is interested in doing the work with me, I'd be more than happy to collaborate. I would also try to factor in the effects of projected adaptation, such as migration. So to recap, so this next slide, this study connects the climate economy and also the climate violence systems by putting forth a new way of modeling carbon externality to endogenize the critical yet previously missing aspect of climate impacts violence. By internalizing such costs in MERGE, which is the methodological contribution of the paper, I find that the optimal carbon price roughly doubles across most scenarios. And for the modeling community, the take-home message is that climate-induced violence may have a material impact on results and should be considered in any model trading off the costs and benefits of greenhouse gas emissions. And I will stop there. Thank you. And I look forward to your questions. And thank you to Steve for helping me play the slides.